All right. So let me increase the volume a little bit. Hello? Asafo Anita, can you hear me?
Yes, sir.
Yes, sir.
Okay, so a quick one. The assignment. A ball is thrown vertically upwards with a speed of 20 meters per second from the top of a tower. Let me forward the question as well. So from the top of a tower, strike the base of the tower in 6 seconds. Okay, find the height of the tower. Take gravity to be 10. Yes, this question, I think a greater percentage of you got it right. So the ball is not thrown from the ground, but it is thrown from the top of the tower. And we don't know the height of the tower. And our task is to determine the height of the tower. So it's always better to get a picture of the question, and then you can use it to estimate or calculate whatever is required of you. So I'm drawing something to represent a tower, which is on the ground. So this is the tower. Okay. Now a ball is thrown from the top of the tower with that initial velocity. So it is thrown just to the maximum height and then drops to the ground. It's not a curvy diagram though, but just something to represent. Well, this is vertically upward motion, so it cannot be a curvy diagram. It falls to the ground. So this is the maximum height reached by the body. The body is going up with an initial velocity stated from the question. So U equals 20. When it gets to the maximum height, final velocity is 0. Okay. In all, throughout a journey, we are told it used 6 seconds. So first, we must know the maximum height it reached. Are you there, class? Are you there?
Yes.
Anita and Co, are you there?
Yes, sir.
Okay, so the time taken to reach the maximum height okay. the time taken to reach the maximum height, of course, is a vertically upward motion. And so it is still initial velocity divided by gravity. And so we have 20 divided by 10, which is equal to 2 seconds. Please, Benjamin, when you come in, please mute yourself for me. So it takes 2 seconds to move from where the top of the tower to the maximum height. Meaning, the rest of the time taken to move from the maximum height to the ground must be 4 seconds. Because, we are told that the time of flight is 6. The 6 seconds. So, we must also determine the maximum height reached. When it was thrown from the top of the tower, what was the maximum height? The maximum height reached, so maximum height reached is equal to u squared over 2j. Or some of you also use this relation ut minus half j/t squared. Then substituted the time, but it can, whether you use this or this, the value will be the same. So if you use this, you have 20 squared divided by 2 times 10, which is equal to 20 meters. Please, what this means is that this distance from the top of the tower to where it's reached, I think sometimes we must use correct sketch to actually explain this. This vertical height from the top of the tower is what we are calculated, which is 20 meters. The height of the tower, we don't know. And that is what the question asks that we calculate for. So this height of the tower, we have no idea. And let that be represented by a capital H. So I know the vertical height from the top of the tower to the maximum height reached, V max, maximum height reached. Okay, that is 20. I've also calculated for the time taken to. So I want the distance it will cover from the maximum height. So when it drops to the ground. So this distance is what I'm calculating for. Let's assume this distance is x. So I must get x. When I get x, okay, this maximum height distance here is also at the same level as what we have here. So if this is 20 meters, then from the maximum height to this point is also 20. So when I'm able to determine x, I will subtract 20 from x to get the height of the tower H. Okay, so it means that x equals height of the tower H plus 20 So if I manage to get x, I'll just subtract 20 from it to get the height of the tower h. So let's first determine h. When a body is falling from the maximum height, it is free falling because initial velocity at that point is 0. So therefore, x will be equal to ut. It is falling vertically downward, so plus half gt squared. U is 0, so x will simply equal to half times 10 times. Now the whole time of flight is 6 seconds, and it took it 2 seconds to move from the maximum height, from the top of the tower to the maximum height, meaning the remaining time that will be taken to move from the maximum height to the ground is 4. Therefore, we have t being equal to 4 seconds, so 4 squared. So it means that we have 5 times 16. And class, what is 5 times 16? What? Pardon?
80.
80. So if x, which is the height from the top, from the maximum height to the ground, is 80, then the height of the tower represented by h will be equal to 80 minus 20. And this is equal to 60 meters. Not difficult question at all. But you see, the question is such that you must take your time to analyze it gradually. You must take your time to analyze it gradually. Else you will not understand. The other method is that, you see, I saw a lot of you using h is equal to 20 times the time of flight, which is 6, minus half times 10 times 6 squared. And they ended up getting minus 60 and took it as minus 60. When you do it this way, I will not mark it correct. It means you don't understand. Yes. Now, the best way to do this is that, you see, it was the throwing of the object was done from the top of the tower. Meaning, initially, the height of the tower isn't part, but it fell and then dropped to the ground. So, other unconventional method of solving this same thing is that if the height of the tower is h, negate, because it wasn't thrown from the ground, you include h, by you negate, make h to be negative. And they are making h to be negative because it isn't, the throw never start from the ground. It was started from h height above the ground. So negative. Then they use ut, which is u is 20, times the time of flight 6, minus half times 10 times 6 squared. And that will give you positive 20. Because this is 120 minus 5 times 36, 180. But because h is negative, when you let h cross the equal sign become positive, we'll have 180 minus 120, and that will still give you 60. But the best method is actually what? This one. How we analyze it, taking the maximum height, time taken to reach the maximum height, and then the remaining time to fall, and then the vertical height reached. Please, is there any question? Is there any question? Okay, let's move on to study of fluid mechanics. Last time we discussed relative density. Okay. So let's continue with upthrust as we were doing. I gave the other question and dubbed it try me. Please, you still try. Take your time, analyze it, and then do it. So upthrust. Please mute yourself for us. Mute yourself. Upthrust or upward force or buoyant force, also known as buoyant force. Buoyant force. These are different terms to describe the same thing. Upthrust is a force which dwells in liquids. So upthrust dwells in liquids. Upthrust is a force produced by liquids or fluids. Please, I'm coming in. Hello. Okay. So upthrust dwells in fluids or liquids. Or gases. When we talk about fluid, we are referring to both liquid and gases. So let me give you a practical experience of upthrust or upward force in liquids. You see, if you have ever tried to lift your colleague while swimming in water, it always feels easy when you try to lift your carry a colleague on your shoulder whilst in water than on land or in air. Please, have you made such observation before? Hello, class. Have you? When you tried carrying your friend whilst in water, it always feels easy than in air. Another observation is that if you have a ball or a balloon and then you try to push the ball or the balloon underwater, okay, so as you exert force on the balloon or the ball in water, The moment you take your hands off the balloon or ball, class, what happens? Class, what happens when you take your hand off? So the balloon or the ball naturally pops up, meaning there is something in water which is always trying to push objects out from the water. And so this upward force produced by water, the example I'm citing is this. This is a ball pushed under water. So this is the force exerted on the balloon. But the moment you take your hands off, you realize that there's a certain force in the water which is always trying to push objects out. This force is the upthrust, the upthrust or the buoyant force or buoyant force. And so when you try to lift a colleague in water, it feels easier because you are supported by the upthrust. You are trying to apply force upward to lift the colleague. And so this force in water or liquids will give you the extra push. Okay. So upthrust exists in liquids. But it depends on some factors. It depends on some factors, which we will discuss later.
Yeah.
Okay. Please, do you have any question? All right. So let's look at how to calculate for this upward force. Manuela, mute yourself when you join. So let's look at how to calculate for this upward force, determining upthrust. Upthrust. There are two different ways of calculating or determining upthrust. The first method is that weigh an object using a spring balance in air. So an object is weighed in air using a spring balance, and the same object is also weighed in liquids or fluids. So we have this as a spring balance. An object is suspended on a spring balance. So this is the weight of the object. Its weight in air is actually the real weight. The weight in air is also referred to as its real weight. Real weight. So weigh the object in air. The weight in air is equal to the object's mass in air times acceleration due to gravity. Now the same object is now weighed when it is partially or fully immersed in water. So we try to weigh the object whilst immersed in water. whether totally or partially. It can be water or it can be any other fluid. Okay. So weight of the object in air or in water is also equal to the apparent weight. So apparent weight refers to the weight of the object whilst in water or in fluids. The observation is that the weight of the object in water or in fluid will be less than the weight of the object in air. So weight in air is less than the weight in liquid. Can somebody tell us why this observation? Why is the weight of the object in air less than its weight in water? Any idea? Yes, Alex.
Because water has a higher density than air.
It's true, but it doesn't convince me as to why the difference. More views. Why is the apparent weight of the object less than its real weight? Yes, more views. Anita. Okay, Giovanni.
Sir, please, because based on the weight of an object in water, if it is light, it will sink. But if it is light, it will float. And if it is heavy, it will sink. So when it enters water, that's why but while the object is in air, that's its normal weight. So that's why the weight is different.
Said, but not so clear. Yes, more views.
Sir, please, the question again.
Why is the object weight in air greater than its weight in fluid, or the other way around? Gideon.
So please, because in a fluid there's an updraft force that is acting on the object.
Exactly. In the fluid, there is an upward force. I said this upthrust is a force which occurs within fluids. So we have an upward force acting against the weight of the object, W. So U is in the upward direction, W is in the downward direction. So the upthrust reduces, okay, or counters the weight, and so reduces it a little bit. So the weight of the object in air or in water is less than in air because of the upthrust. Frank.
So is the upthrust force stronger than gravity?
No, it's not stronger, but it tries to reduce it a little bit so that it is like, Frank, you being hung on something and something trying to push you up a little. So that reduces your actual weight in the water. Elegant.
Sir, please, you said the weight of an object in water is less than the one in air, right?
Yes.
Sir, please, but what you've written here, you've written the weight is actually less than the weight.
Weight in air, thank you, is rather greater. weight in air is greater than the weight in liquid, or the weight of the object in the liquid is less than the weight in air. Okay, and this explains the reason why when you try to lift somebody up in water, it is easier, because in water you are supported by an extra force, which is the upthrust produced by the liquid. Class, are we okay?
Yes, sir.
Yes, sir.
So we have weight in air minus the weight in the fluid or the liquid being equal to the upthrust. So let's assume when the object is weighed in air, it weighs 10 Newton. When it is weighed in liquid or fluid, it weighs 8 Newton. It means that the difference is equal to the upthrust. So upthrust can be determined by determining the real weight minus the apparent weight minus the apparent weight. So that this is one important equation we'll be using. Okay. Another method of doing the same thing is that this time, instead of using a beaker, I want to use Eureka can. Using the Eureka can method. No. Good morning. Hi. Are you Archimedes? Okay, yeah. Eric, Ibia. Normal way, yeah. Okay. That's it. Hello, Frank.
Sir, please, did you say that the weight in air is less than the weight in liquid?
The weight in air is greater than the object's weight in liquid. This is it. The first one. Or the weight in liquid is less than the weight in air. Frank, are you okay?
Yes, please.
So with the Eureka can method, it is the same setup. But this time, the Eureka can has a spout. Let me give a quick sketch. This is our spring balance. The object is weighed. This time, when it is totally immersed in a can, Eureka can. The Eureka can has a spout. It is actually filled to the level of the spout. The idea is that this time we want to collect the volume of the water that will be displaced. So the excess water passes through the spout and it's collected in a beaker. This is the Eureka can. Okay. So at the moment the metal or the solid or object is immersed either partially or fully in the water, water will be displaced. Water will be displaced. We are interested in the weight of the displaced water. So weight, we determine the weight of water displaced. Okay, so the object is gradually immersed, and when the water overflow stops, we weigh the beaker when empty and weigh the beaker plus the water, and then subtract to get the weight of water displaced. Now, when this experiment is done carefully, it will be observed that the weight of the water displaced is always equal to the difference between the weight of the object in air and the weight of the object when it is immersed in a liquid. So here we have weight in air minus weight in liquid equal to weight of water displaced. Water displaced. So that's the second method of determining upthrust. So, all right. All right. So that is how to determine upthrust. Two methods. Weigh it in air, weigh it in liquid. Subtract, and the difference is equal to the upthrust. Or weigh the object in water or liquid and then determine the weight of the displaced water, and that is equal to upthrust. So here we have upthrust in two different ways. Real weight minus apparent weight equal to upthrust, and we have the same thing also equal to upthrust is also equal to weight of liquid displaced. This is also equal to upthrust. This observation gives us a very important, this observation of upthrust gives us a very important principle in fluid mechanics known as and not me online. This gives us or introduces us to what we call Archimedes principle. Archimedes principle, which is a very important principle under physics. Archimedes principle states that whenever a body A body is fully or partially immersed in a fluid. It experiences an upthrust, which is equal to the weight of fluid displaced by the body. All that Archimedes is saying is that upthrust on a body immersed fully or partially in fluid is equal to the weight of fluid displaced by the body. That's all. This is Archimedes' principle. Class, are we okay? Class, are we okay?
Yes, sir.
So, as disciples of physics, please, you do not forget Archimedes' principle. When you are asked, you must be able to tell that a body which is fully or partially immersed in fluid experiences an upthrust which is equal to the weight of fluid displaced by the body. So simple. And this principle is very, very important in flotation. So we'll go deeper and then look at applications of flotation, and you understand how important this principle is. Please let me take attendance and then get back to you, okay? Just for 1 minute or two, and I'll get back. Anita, don't forget to remind me 20 minutes to close. So at exactly 20 minutes of closing, please remind me to share so that we can have the evaluation. Okay. So back from commercial break. Do we have any question? Okay, so Priscilla, what is okay, Frank?
Sir, please, so the Archimedes principle, is it based on the Eureka can method or just the normal?
It can be both. Both are ways of determining upthrust. Okay. The important thing is that upthrust can be determined in two different ways. By weighing it in air, weighing it in fluid, and then subtract. When you subtract, the difference is equal to the upthrust. And we can also use the Eureka can method. We collect the water displaced and weigh it. The weight of the water displaced is equal to the upthrust. So Archimedes is only saying that if a body is fully or partially immersed in fluid, it would experience an upthrust. So this one, Frank, yes, is exclusively used or goes in line with when it is weighed in fluid. When it is weighed in fluid and then the upthrust being determined. Is that okay?
Yes, please.
All right. So, Elikem, what is Archimedes' principle?
Archimedes' principle says that whenever a body is fully or partially immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced by the body.
Thank you. So, you see, the problem is that most students mistakenly take it, when a body is immersed in fluid, the volume of fluid displaced is equal to the volume of the object. Volume of fluid displaced is taken to be equal to volume of objects, which is true. But students usually mistaking this for upthrust. When a body is fully or partially immersed in fluid, the volume of fluid displaced is equal to the volume of the object. This is not Archimedes' principle. Archimedes' principle is about the upthrust being equal to the weight of fluid displaced class. So take notes and then have a better distinction. All right. And so we have upthrust equal to weight in air minus weight in fluid. We have the same upthrust also equal to weight of fluid displaced. They are all upthrust. What it means is that we can always equate this to this because they are all upthrust. Real weight in air minus weight in, let me use liquid, is equal to weight of liquid displaced. And we are equating them because they are all upthrust. Okay. Now, because weight is equal to mass times acceleration due to gravity, We can also say that weight in fluid equals mass of fluid times acceleration due to gravity. So we are equating upthrust, weight in air, minus weight in fluid or liquid to be equal to mass of fluid displaced F times gravity. So here MF equals mass of fluid displaced. Mass of fluid displaced. Class, are we okay? I hope we are okay here.
Yes, please.
Okay. Then Giovanni,
Sir, please, I don't get why the mass of fluid times gravity. I don't get that part.
Giovanni, weight of a body. If I want to determine your weight is your body mass times gravity. So if we are talking about weight of fluid displaced, then we can also equate this to the mass of the fluid times gravity. Are you okay? Because weight is mass and gravity. Giovanni, is that okay?
Sir, no.
Oh, the weight of something is the something's mass multiplied by gravity. So if I have the mass of a body and then I multiply that by gravity, it is equal to the weight of a body. Alikem. Hello, Alikem.
Sir, please, does that mean we can say that after is equal to the mass of fluid times gravity?
Exactly. Upthrust is also equal to mass of fluid displaced times gravity. But don't forget, mass of the fluid displaced by the body or the object. Okay. So, Giovanni, your body weight is equal to your body mass times gravity. And this is the reason why a fat person can weigh more than a slim person. This is because the fat person has greater body mass than the slim person. Giovanni.
Sir, please, then why is it equated to the weight of air minus the weight of liquid?
That is also upthrust. Upthrust can be two. Weight in air minus weight of the body in liquid or fluid. And upthrust is also equal to weight of the fluid or liquid displaced by the same body. So you, Giovanni, I weigh you in air. That's your weight in air. Then the same Giovanni is weighed in water. That is your weight in water. When I subtract your weight in water from your weight in air, that is upthrust. I can get the same thing, okay, if I submerge you, weigh you in water, but this time collect the volume of water that will be displaced and weigh. When I weigh the volume of water you displaced, it must be equal to the upthrust. So if you weigh 10 Newton in air and you weigh 8 Newton in air, it means in water, it means the upthrust is 2 Newton. When I collect the volume of water you displaced when you were being weighed in water, and I determine the weight, I must also get a figure close to 2 Newton. So weight of objects, weight of liquid displaced is also equal to the upthrust, which is weight in air minus weight in fluid. Are you okay?
Yes, sir.
That is why I'm equating the two here. Look at this. This one is upthrust, weight in air minus weight in fluid, and this is also upthrust. So they are the same. Are you okay?
Yes, sir.
Are you sure?
Yes, sir.
Okay. So as I was saying, our weight is just our body mass times gravity. So a fat person would weigh more than a slim person, because the fat person has a greater body mass than the slim person. Okay. The only point or time where a slim person can weigh more than a fat person is when the slim person is very tall. When the slim person is very tall, there is a possibility that he can weigh than somebody who is fat. This is because it is as if his fatness has been stretched, and that is what has contributed to his height. So it's like compact fat person, but this time around it is being stretched to increase in height. So our weight is directly proportional. Weight is directly proportional to mass. And don't forget, gravity is constant. So when mass increases, weight will also increase. Are we okay? So that is why we are equating the weight of water or fluid displaced to be equal to the mass of the fluid displaced times gravity. Class, if you have any question, ask before I continue. The ladies among us ask questions. Anita, let me look for them. Ida, Ablina, and the rest of you. Anna, ask questions. Lydia, you are here. Daisy. Only the guys are asking questions. Okay, Frank.
Sir, please, can you explain how the weight of the fluid displaced will be given?
I don't get your question. Come again.
Like the weight of the fluid displaced, like how is it like stated in a question?
Oh, no, I'm doing the theory with you. At the end of it, we'll solve questions. So you don't worry about how it will be stated. Okay.
Okay, sir.
All right. So upthrust, the same upthrust is also equal to mass of the fluid displaced or liquid times gravity. We can also express mass in terms of density and volume. Of course, density is mass over volume. And so it means that mass equals density times volume. So Giovanni and the rest of you, we want to express the mass of the liquid displaced in terms of density, meaning this is also equal to density of the liquid displaced times volume of the liquid displaced. So when we substitute this for mass of liquid displaced, we have upthrust equal to density of the liquid displaced times volume of the liquid displaced times gravity. So upthrust is simply rho Vg, rho Vg, rho Vg. But you must take note that where rho is the density of the liquid displaced, V is the volume of the liquid displaced, and gravity. It means that on the surface of the earth, upthrust depends on two key components. Upthrust is directly proportional to density of the liquid. Upthrust is also directly proportional to volume of liquid displaced. LHM.
Sir, please, can you please take from the upthrust is equal to the mass of liquid and gravity?
You see, upthrust equals mass of liquid displaced times gravity. But we can also express mass in terms of density and volume, because mass is density times volume. So we can say that the mass of the liquid displaced equals density of the liquid times volume of the liquid displaced. So that upthrust is equal to density of liquid times volume of liquid displaced times gravity. Are you okay?
Yes, sir.
Frank.
So the weight of the fluid is the mass of the fluid times gravity.
Yes.
How is the upthrust the same thing as the weight of the fluid?
Archimedes principle. When a body is fully or partially immersed in fluid, the upthrust experienced by the body is equal to the weight of fluid displaced. So that is why in our experiment, we weigh the object in air, weigh it in water, and we also collected the volume of water displaced. We weighed it, and the value is the same. Okay, so upthrust is equal to the weight of fluid displaced by a body immersed in fluid. So, Frank, that is why we are equating the two.
So the principle states that the upthrust is equal to the weight of the fluid.
The weight of the fluid displaced. That's all.
Okay, sir.
Giovanni.
Sir, please, I don't get how upthrust is equal to density times volume times gravity.
Giovanni. Yeah, but they are up. You were not following. Yeah, we earlier established that upthrust equals what? From Archimedes' principle, you want to say upthrust equals what, Giovanni?
Sir, please, the fluid displaced by the body.
Weight of the fluid displaced. Do not forget the weight. Very, very important. So upthrust equals weight of fluid displaced. How can you calculate weight of a body? Giovanni.
Mass times gravity.
So if we have weight of fluid displaced, then it can also be mass of fluid displaced times gravity. So that's how come we change weight to mass of fluid displaced times gravity. So upthrust is weight. Upthrust is also mass of fluid displaced times gravity. Then we know mass is also density times volume. So the mass of the fluid displaced can also be expressed as density of the fluid times volume of the fluid displaced. Giovanni, this is it. Please, do we have any other person with that challenge in understanding this? So it is a gradual build-up from Laplace equals weight of fluid displaced, then weight is changed to mass of fluid displaced and gravity. Mass of fluid displaced is changed to density of fluid times volume of fluid displaced. Giovanni, are you okay? Giovanni,
Yeah.
are you okay?
Yes.
So it's not difficult. It's a build-up from scratch. Anita, are you fine? Your line is even breaking. So look at the three equations. Laplace equals weight in air, real weight minus apparent weight. And this is also equal to weight of fluid displaced. This is also equal to mass of fluid displaced times gravity. This is equal to density of fluid times volume of fluid times gravity. So finally, we realize that Laplace is directly proportional to density. Laplace density of the liquid. Laplace is also directly proportional to the volume of fluid or liquid displaced. As for gravity, it is constant on the surface of the earth. So this wouldn't change. Gravity will not change. Okay? Meaning that when density of the fluid increases, Laplace would increase. When density of the fluid decreases, Laplace would decrease. And class, this explains the reason why Laplace is greater in water than in air. The density of air is about 0.00012 meter cube, and the density of water is 1.0 gram per, this is gram per cm cube, sorry. And the density of water is 1.0 gram per cm cube. So because density of water is greater than density of air, Laplace in water will be greater than Laplace in air. So Laplace depends on the density of the fluid. Laplace is also directly proportional to the volume of fluid displaced. This also explains why a ship can float, but a small stone will sink in water. A ship can float in water because the ship is designed to have large volume. It's designed to have large volume so that it can always displace large volume of water. Because when the volume of water displaced by the body, which is the ship, is large, the Laplace which would enable the ship to float would also be large. So that is why ships float in water, but stones sink, because the volume of stones very small, and so it will just displace small volume of water. And when the volume of water displaced is smaller, the upthrust which will enable stones to float will also be smaller, and so it will sink. Didier?
Sir, please can you come again?
Okay. The reason why ships float in water, but small pebble or stone sinks is that the ship is designed to have large volume. It has large volume within. Once the volume is large, it means it can, when it is placed on the sea, it will displace large volume of water. Okay, upthrust too depends on density of the liquid times volume of the liquid displaced times gravity. So once the ship is designed to have large volume, okay, it will displace equally large volume of water, and so it would increase the upthrust it experiences. Meanwhile, a small stone dropped in water would only displace small volume of water. So when the volume of water displaced is smaller, upthrust would also be smaller. And the upthrust is what supports it to float. So when the upthrust is smaller, it means it will sink. Elikem.
Sir, please, does that mean that if the stone is also big and has a large volume, it doesn't mean it will float?
So that is why you see, when you place empty tin of milk on water, will it sink or float?
Float.
You see, the empty tin of milk is also a solid, but part of the solid has been scooped out so that large volume is created in it. By scooping part out, it reduces its density and creates huge volume. And so it's able to displace greater volume of water than when it's a complete solid. So if you could scoop some portion of stone out so that you create large space in stone, it can sink in water. Are you okay? Davis? Ella?
So can you also see that?
Ella, your voice is down. Can you increase? Come close.
Sir, please, can you also see that when an object is hollow, it can thereby displace a large amount of water, thereby causing it to float?
Exactly. The hollowness is due to the volume in it. It is hollow because there is large space in it. Is that okay? So our canoes are designed in such a way that it is the compact trees we have around. But when the tree is cut, the canoe covers chop some of the wood from it and create a hole. They're doing that means that they want to create large space or volume in it so that the canoe can displace large volume of water, because the volume of water displaced is what produces the upthrust. The upthrust, you cannot change the density of the seawater because it's natural thing, but you can control the volume of water the object displaces when it is put into it. And so the idea is that let's create space within, large space within, so that it will create large volume, and so the volume of water displaced will be large. When the volume of water displaced is large, it would increase the upthrust, which will enable it to float. That's the whole idea. So upthrust experienced by objects is directly proportional to the density of the liquid. The greater the density, the greater is the upthrust. And the lesser the density, the lesser is the upthrust. Upthrust is also directly proportional to the volume of fluid displaced by the body in the fluid. So the greater the volume of fluid displaced, the greater is the upthrust. And the lesser the volume of water, the lesser is the upthrust as well. Please, are we okay? Ask more questions if you have one. The questions are very important. Didier, you are boy. I can see. Didier Drogba. All right. Nana Kumi, Elita, ask a question. Anita, ask one. Emirat, ask question. Anna, Priscilla. So if you are asked to explain why ships float, but stones sink in water, it has to do with the volume within, which creates the upthrust. Is that clear?
Yes, sir.
Okay. So let's derive our equation. So we see upthrust appearing in two different or three different forms. Upthrust equals weight in air minus weight in fluid. Upthrust is also equal to weight of fluid displaced. Then upthrust is also equal to mass of fluid displaced times gravity. We can therefore equate, and then finally, upthrust is also density of the fluid times volume of fluid displaced times gravity. These are all relations for upthrust. So depending on the parameters a question gives you, you can choose the one which will fit it suitably. Because of this, we can also equate weight in air minus weight in fluid to rho Vg, where rho is the density of the fluid, V is the volume of fluid displaced, then gravity. Now, you see weight in air. Giovanni and Co, open your eyes. I'm developing another relation. This is up. The left-hand side is upthrust. The right-hand side is also upthrust. But I'm going to develop another form. Weight in air is mass in air times gravity, isn't it? Then weight in fluid is also mass in fluid times gravity. This is equal to the upthrust rho Vg. We can factorize gravity out so that we have mass in air, real mass minus mass in fluid, which is apparent mass, times gravity, equal to rho Vg. Gravity at the left-hand side, gravity at the right-hand side. So we have mass in air minus mass in fluid equal to rho V. J has cancelled out. Class, what is rho V? Rho times V. What is it?
The mass of the
Mass of the mass of the
of the object.
Of the fluid, of the
Fluid
fluid
displays.
display.
Displayed.
Okay. So we also have mass in air minus mass in fluid also equal to mass of fluid displays. We can break apparatus down to this as well. So take notes.
Okay.
Okay. We can also break apparatus down to this. So these are the fallouts from Archimedes' principle. And please, as I said earlier, take note of the equations we have actually derived so far. We'll be using them in solving problems. And let me demonstrate, solve simple question on apparatus with you so we can continue from next week. I'm giving a hand, Ella, Davis, Ella.
How did Archimedes come about this principle?
By experiment. You see, there is a history behind it. And the history is that, Anita, don't forget to 20 minutes to closing to draw my attention. Right?
Yes. Okay.
The history is that Archimedes was a renowned physicist, scientist, and all that is during his time. Then one day, the king of Sicily, one of the places in Greece, gave a certain quantity of gold to a goldsmith in order to make a crown for him. Upon return of what the goldsmith designed or made with the gold given, the king suspected that the goldsmith had stolen parts of the gold because he felt whatever he was given felt so light. And so by just weighing the two, he could see that no, the guy had duped him by stealing part of his gold. But who are you to judge? You can't just look at it and then accuse. And so, in order to get the truth, he called Archimedes to find a way of, finding the truth of the whole thing. So, Archimedes had not even solved such a problem before. And so it was a burden to him. And history says it that Archimedes one day went to a public bathhouse that has a jacuzzi type of bath where the basin has to be filled with water and then immerse himself either fully or partially in it. And so when Archimedes did that, he realized that some volume of water was displaced when he got himself immersed either partially or fully into the water or inside it. And so it gave him a clue that he could use that to, get the truth of the king's problem. Because when an object is immersed in water, the volume of water displaced is equal to the volume of the object. And that is how come in your EHS lesson, when you are asked to determine volume of irregular objects, you tie it to a stone, immerse it in a measuring cylinder, indicate the initial reading, and after immersion, to determine the final reading on the measuring cylinder, you subtract initial from the final. So that gave birth to the idea. So Archimedes used that idea to, determine volume of the gold that was given to the man, and determine the volume of the crown, and then realized that there was huge difference between the volume produced by both. And so he based on that alone to answer the king's problem. And the guy actually confessed that, yes, he took part of the gold. Then afterwards, it was developed upon. And that is how come Archimedes got the famous Archimedes principle, which says that when a body is fully or partially immersed in fluid, it experiences an upthrust, which is equal to the weight of fluid displaced by the body. So, Ella, this is your answer. So, it was based on extensive experiments. He did not just stumble into it. He conducted experiments and then, as a result, saw this. All right, let's answer a question, and I'm reading. An iron cube of volume 800 cm cube. An iron cube of volume 800 cm cube is totally immersed in water. A, in water. B, in oil of density 0.8 gram per cm cube.
Please go over.
An iron cube of volume 800 cm cube is totally immersed in A, water of density 1.0 gram per cm cube. Density of water 1.0 gram per cm cube.
Sir, please, can you go over?
Can I? An iron cube of volume 800 cm cube. So the volume of the iron cube is 800. Is totally immersed in A, water. Is totally immersed in A, water of density 1.0 gram per cm cube. B, in oil of density 0.8 gram per cm cube. And C, in oxygen gas 0.0015 oxygen gas of density 0.0015 gram per cm cube. Calculate the upthrust in each case. Calculate the upthrust in each case. Okay, so we have to determine the upthrust in each case. Okay, so quick one. Upthrust is equal to weight of fluid displaced, rho Vg. This time we cannot use real weight minus apparent weight because that's not the information we have. So we can only use rho Vg, where rho is the density of the liquid, V is the volume of the liquid, and G is gravity. Yes, G is equal to 10 meter per second squared. Now, for the first question, water. The water density of water is 1 gram per cm cube, which is also equal to 1,000 kilogram per meter cube. So 1,000 times, when a body is immersed, fully immersed in fluid, the volume of the body is equal to the volume of water displaced. And so we are told that the iron cube has a volume of 800 cm cube. That is also the volume of the liquid displaced because it is fully submerged in it. Now, since I'm using SI units of this in kilogram per meter cube, I must also change the volume to meter cube. So 800 times, I'm using the parenthesis method, centi. Centi is 10 to the power negative 2 m meter, all raised to the power 3. So this will be 800 times 10 to the power negative 6 meter cube. So it means that 800 cm cube is equal to 8 times 10 to the power negative 4 meter cube. That's the conversion of cm cube to meter cube. I think I have to spend time to teach you this so that you can master properly. So 8 times 10 to the power negative 4 times acceleration due to gravity is 10 meter per second squared. So times 10. When I put them together, I have 10 to the power 4,000 times 10 times 8 times 10 to the power negative 4. 10 to the power 4 times 10 to the power negative 4 is equal to 10 to the power 0. So I have 8 times 10 to the power 0. 10 to the power 0 is equal to 1. So the answer is 8 Newton. So for such volume of cube, the upthrust in water will be 8 Newton. Can you try the second one? We are going to use 20 minutes for evaluation or less. That is why I'm actually speeding. Giovanni.
Sir, please, why is the 1,000 raised to the power 4?
Oh, I have 1,000 times 10, and 1,000 times 10 is equal to 10,000. 10,000 is equal to 10 raised to the power 4. Giovanni, are you okay?
Yes, sir. Sir, please, why can we choose to calculate for it in grams per centimeter cube?
Yes, but you see, I'll do that with you next week. Since we are going to, I'll teach you how to use the gram per cm cube, right? Okay. We are going to go through the evaluation. That is why. So you relax. We've just started an Archimedes principle. I'll take you through all that. Okay.
So before you were solving the question, we use 10 to the power negative 4.
Yeah. You see, when I converted the volume, I had 8 times 10 to the power negative 4. So that is the volume. Then the density and gravity gave me 10 to the power 4. So it's like having 10 to the power 4 times 10 to the power negative 4. This is equal to 10 to the power 4 minus 4. And that is 10 to the power 0. 10 to the power 0 is equal to 1. So that's how come I got 8 Newton. Are we okay? So you, as I said, relax. Let's go through our evaluation. We'll be answering sample questions. I'll give you the other side of this same thing and you'll be smiling, okay? Okay, class, I've just sent the evaluation form to the platform. Please, let's all open it, tap it, and then let's go through it together. Each one of you, please tap on the link and let's open it together and then finish this evaluation for physics. I am opening it, so please, each one of you must do so for me. We spend time to teach you, and so you must evaluate us. This is very, very important as part of the best practices of Omega. And so do not sit on the fence. Please get involved. We are about 50 here. Each one of you should do so. So the heading is Omega Teacher Evaluation. Hello? Can you hear me? Emelda. Emelda, your hand is up. Class, can you hear me? Alikam. Frank. Hello? Hello? Hello, Gideon. Ella. Class, can you hear me? Hello?
Yes, please.
Okay, so please, let's go through it together. So, the first, I'm sure you've done this before. Class, have you done this before? Oh, let me
Yes, please.
Okay, so let's go to
Yes,
the
sir.
first. Let's go through the first one. So 1, links to joining the class are shared before the scheduled start time. So A, never shared before. B, sometimes shared. C, often shared late. D, always shared before time. So pick the one which is up. Hello. 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 I'm coming. Okay, so the second question is that does the teacher skip classes? Does the teacher skip classes? A, skips class most of the time. So B, C, please go through it and then pick the one that is applicable to your physics teacher. Okay. So you just tap on it. Tap on the option. Then 3. Give the number of times the teacher has skipped classes. Give the number of times the teacher has skipped classes. So you pick the one which you think is applicable. 4. Teacher makes alternative arrangement if he or she is unable to attend classes. A, never makes any alternative. B, sometimes makes alternative arrangement. C, has never skipped classes. So pick the most appropriate one. 5. Teacher is willing to answer your questions privately after lessons. A, never answers. B, ignores my private questions. C, sometimes answer my private questions. And D, always answers my private question. Pick what is applicable or suitable to the teacher. Then 6. Are reasons given for not answering your questions privately? A, no reasons given. B, sometimes reasons are given. C, yes, reasons are always given. D, not applicable.
Sir, not applicable means what?
This particular question does not apply to the teacher. 7. Teacher's voice is very clear during class session. A, voice is always low. B, voice is sometimes clear, other times not clear. C, voice is most often I think sometimes clear. I think this is wrongly. And then D. So pick what is applicable. 8. How clear are writings and illustrations on board and screens? A, handwriting is not clear. It is difficult to read. B, handwriting is sometimes not clear. C, handwriting is clear at all times. So pick it and do the needful. 9. Background of the teacher during lessons is always noisy and disruptive. B, sometimes noisy. C, always quiet throughout the lesson. Then 10. The teacher gives assignments on topics taught. A, never gives. B, occasionally. C, often gives. And D, always gives assignments. Pick the one that is so appropriate. 11. Teacher marks assignments promptly and gives feedback for improvement. A, never. B, occasionally. C, marks some and leaves others. And D, always marks and gives feedback for improvement. 12. How many exercises, tests, assignments, homeworks, or group works, etc. have been given by the teacher? So you have the string, the A to F. Pick the one you think is applicable here. 13. My level of understanding of what is taught is A. I do not understand most of the time. I understand. B, I understand some of the concepts. C, I understand most of the concepts. And D, I have excellent understanding of all concepts. 14. Are videos of lessons shared with you? A, never. Never shares video. B, sometimes. C, shares video on all lessons. 15. Rate the stability of teachers' internet connectivity. A to D. Pick one. Connectivity is always bad. Network drops too frequently. Network drops occasionally, and network is consistently stable throughout the lesson. And 16. Hey, the method used in the lesson delivery is less interactive, quite interactive, very interactive, and excellently interactive. I'm sure you understand interactiveness here. 17. Would you like to maintain your teacher? A, no. I wish to have a different teacher. B, maybe. C, yes. I will always like him or her to teach me. 18. It's 18 is more or less like, will you join Omega vacation classes in your next vacation holidays? A, no. I will join. No, I will not join Omega. B, I'm not sure if I will join Omega. And C, yes, I will definitely join Omega. 19. Did the teacher meet your expectations? A, no, my expectations were not met at all. B, yes, my expectations were somehow met. Yes, my expectations were met to a large extent. And D, yes, my expectations were excellently met. 20. Any other comments about the teacher? Over to you, Yola. Here is over to you. And 21. Any other comments for Omega management? When you finish, please submit. If you don't submit, all that you spend time to do becomes futile or comes in vain. So after doing all that, do not forget to submit. We are 47 now. So we expect 47 responses from each one of you. So I'm waiting for you to put your comments on 20 and 21. Then you submit to end the show. I'm waiting for you.